Okay, let's work pathways problem 6.57. Asks us to consider this reaction. 1/8 of S8 plus H2 to make H2S. We are given an enthalpy of reaction, delta H, of negative 20.2 kilojoules for this reaction as it is written. We're asked a sequence of questions that are basically aiming at developing your understanding of what that delta H number means and how it scales with the quantity of reactants. Okay? So in part A, we're asked whether this reaction is exothermic or endothermic. And this is a simple, easy question, right? What determines that? Well, the sign on delta H determines it. If it's negative, as it is here, the reaction is exothermic. Okay? If this was a positive 20.2 kilojoules, as it's written, that would be endothermic. So if this is positive, endothermic. If it's negative, exothermic, just by definition. Okay? Easy, easy, easy. Part B asks us, what about the reverse reaction? Okay, so in this one, I have S8 and H2 as my reactants, and this is my product. What if I take this and decompose it into the elements? In other words, I flip-flop what is my reactants and my products. What would happen to the sign on the delta H? Would it be endothermic or exothermic? Well, in this case, if you flip reactants and products, you also flip the sign on delta H. So this plus this to make this is exothermic. If you flip-flop it, the reaction becomes endothermic. All right, so not a big surprise. If you flip-flop things, it makes sense the sign is going to change. Now, another way to know that, even if you didn't know that if you flip the reactants and products, you flip the sign on delta H, it would be a decomposition reaction where bonds are being broken. Oftentimes, frequently, I guess I could say, those are endothermic, particularly if you go back to elements. Okay. All right, so moving on. Part C. What would be delta H equal to if 2.6 moles of the S8 reacts? Okay. Now, this gets into your quantitative understanding of what this number means as it's written. It's describing the enthalpy change of this reaction as it is written, which to me indicates 1/8 mole of this with 1 mole of this to make 1 mole of this. The associated enthalpy change is negative 20.2 kilojoules if I combine things in those exact numerical ratios. Okay. Now if I change that ratio, my delta H changes. Okay. Note that this is not kilojoules per mole, it's kilojoules as it's written. Okay. So if I scale the reaction up, I could expect to get more heat involved perhaps, or my enthalpy change would be different. All right, so how in the world can I compute how much different it's going to be? Okay. Well, I think what I need to do to help me with this is to figure out how much I've scaled my reaction up. Okay. In this particular case, I'm scaling it up to 2.6 moles, when originally it was far less than that, okay? Originally, I had 1/8 of a mole. Now if I do conversion to decimal form, 1 divided by 8, that yields 0.125 moles. So it turns out that what I'm doing here is I'm basically scaling up my reaction by this ratio. Now, if I compute that, it looks like here on my notes sheet, I've scaled up the reaction by about 20.8 times. Okay? So it stands to reason then to compute delta H. All I need to do is multiply that scale-up factor by my stated enthalpy of 20.2 kilojoules, okay? And if I do that, it looks like I get negative 420.16 kilojoules, 0.2 kilojoules, okay? So the main idea for this problem then is that if you, or for this part of the problem, is if you change the amount of material that's reacting, you also change the amount of heat that's transferred. Okay? Lastly, in part D, we're asked specifically about 25 grams of S8 reacting. Okay, 25 grams. So this is in grams units. This is an eighth of a mole. I know if an eighth of a mole reacts, this is my enthalpy change. So I don't really know where I stand right now because I have incompatible units. Right, I've got grams here, and I've got moles up here. But if I could take my 25 grams of S8, one of my reactants, convert that into mole units, then I could compare apples and apples. So that's what I'm going to do. Okay. So 1 mole of S8 has a particular mass associated with it. And if you go to the periodic table and you multiply sulfur's atomic mass by 8, because we're dealing with the S8 here, you end up getting 256.48. This suggests I've got 0.09747 mole of my S8 that I'm reacting. So now that I've converted to moles from grams, this problem is very, very similar to what we had here in problem C. In problem C, we had this many moles of S8. Now we've got 4 less than that. Okay, so we expect the delta H to be probably a smaller number. Okay, but we know how many moles we've got, and we've either scaled up or scaled down the reaction system. Now I think in this particular case we might have scaled it down a little bit, okay? Because I've only got 0.09747 mole of my S8, and as it was written, it corresponds to 1/8 of a mole, which again is 0.125. So my scaling down factor essentially is 0.7798. So I'm only about 78% of how what it's written. I've scaled down the reaction a little bit. But the beautiful thing about this knowledge is that since I know my scaling factor, I can now multiply that by my negative 20.2 kilojoules, which results in the realization that negative 15.75 kilojoules is what I'm going to expect as my enthalpy change for part D. All right. So key ideas here: identifying exothermic and endothermic reactions. This is pretty easy. Just a sign on delta H. If it's negative, it's exo. If it's positive, it's endo. Reversing the reaction, you flip the sign. Simple as that. And then in parts C and D, we relied on the knowledge that this delta H value, if it's not per mole or some quantity specified, okay? Sometimes you see that, okay? It's like written as per mole. But in this case, it's specified for the reaction as written. And because of that, it will scale up or scale down depending on how much of the reactants we've got.